Hey, everybody. Will Ainsworth. Taylor.
Here.
Brody.
Here. Ah.
Joe Bevilacqua.
Here.
Joe Blakely.
Yeah, I'm here.
Ryan.
Here.
Drake. Charles DiPasquale.
Here.
Martin. Dimitri. Dejor.
Present.
Present. Dude has class. Bobby.
Here.
Bailey.
Here.
Hussein. Owen.
Here.
Alex. James Johnson.
Here.
Brooke.
Here.
Jack Kenny.
Here.
Elias.
Here.
Matt Lehman.
Here.
Mike Mendola.
Here.
Paige.
Here.
Matt Morgan.
Here.
Brandon.
Here.
Connor O'Brien.
Here.
Matt O'Donohue.
Here.
Shane.
Here.
Jesse. Ryan.
Here.
Zoya. Marco.
Here.
Grace.
Here.
Nick Slattery.
Here.
Carrie.
Here.
Chris Starkweather.
Here.
David Styria.
Here.
Sean.
Here.
Okay, how is everyone today?
Good. I'm here too. You didn't call my name.
Thank you, Nolan. Okay, gang. What a wonderful Tuesday we have. Anybody have questions? Notice I'm at St. Bonaventure University. Oh, God bless.
Thank you.
Yeah, so I'm at St. Bonaventure University if anybody wants to stop by. So let's get on with our lives here, yeah? I want to finish up talking about So this is our Moodle, right? Are you looking at my Moodle?
Yeah.
But Nolan Toft, you got to be the spokesperson and say, yeah, we are, or no, we're not.
Yeah, we can all see it.
You're looking at my Moodle, right? So you guys are familiar with these videos that I've put up here, right? Because you've been playing with R and learning how to do it and stuff like that, right? So this was all the chapter 1. This is all out of Wooldridge. And this is the math review that we have been working on. It's not in Wooldridge, it's in a different textbook, right? But you have all these resources that I've put up here, right? So the solutions to the problems, you asked me to put them up there. The review sheet from lecture, and then my own notes. Of course, I record all of our gatherings here. So I also put these 2 codes up here. Well, this is code and this is data. And I'm gonna visit this in a few minutes, okay? Basically, let's have a look at these slides. This is from a Brooks, I think it's Oxford University Press. So Nolan, you're looking at the slides from Econometrics for Finance, right? So one of the things we talked quite a bit about was matrices and things that I wanted you all to do in matrices, right? But in particular, I wanted to talk about, I did talk about using matrices for portfolio theory, because this is, of course, a financial econometrics class. And we talked at one session, it might have been the last or the one before, about portfolio theory and putting these things together, right? So this is slide 53. Talks about creating a variance and covariance matrix, how to construct that, right? We want to calculate the variance of returns on a whole portfolio, even though maybe that portfolio is just 1 or 2 stocks, right? But we can do that in matrix form. The transpose of weights times the V that you created, a scalar, times the V is the matrix. Here, the variance covariance matrix, don't confuse that with V sub P, which is the variance of the portfolio. So this is slide 56. And then, of course, you can do this also by doing correlation. And the matrix algebra associated with doing this would be the variance of the portfolio, the transpose of the weight times S is a diagonal matrix containing standard deviations of portfolio returns. And C is your correlation matrix of returns, and W, right? So this is a different methodology for doing what we did here, okay? In other words, what they're telling you is this V must also be equal to SCS, okay? So, and then the slides go on. So essentially those 4 slides, right? 53, 54. And on Moodle, I put in notes, particularly about slide 53. Yeah. Slide 54. This is how to do a variance of a portfolio longhand, right? So slide 53, slide 54, slide 55, construct a matrix of actual returns, right? So V, the returns here, and now recall we're after VP. Use the variance covariance matrix V to calculate the portfolio variance VP by using weights W. Something like this, where you have weights of different stocks, the variance covariance matrix, and the transpose of the weights. Effectively, we need to transpose so that we can have variance and A squared, right? In our variance of the portfolio formula. How many feel all kinds of happy about learning that? Not yet?
I'm very confused on what we're doing.
We're constructing the variance of a portfolio using matrix algebra.
Do you have like an example you could go through?
Yes, so we started with this. Portfolios with stocks, just stocks and bonds, with the weight in each. So the return of that portfolio would be the weight or the amount of money you have in stocks times the return of stocks plus the weight or the amount of money you have in bonds times the return in bonds. Oh, sorry. You couldn't see that, could you, James?
No.
We're using matrix algebra to calculate the variance of a portfolio. If you have a portfolio with just two items in it, stocks and bonds, the return on your portfolio here, R sub P, would be the weight that you have in stocks times the return on stocks, plus the weight that you have in bonds times the return on bonds. Does that make sense?
Yeah.
You can't do that when you're talking about variance. Variance is a whole different ballgame because the variance of the sum of two products, the variance of AX plus BY, is not as straightforward as the return of stocks and bonds.
When it says AX plus BY, what is that talking about?
It's the sum of two products. It's a rule in statistics. In other words, this is the sum of two products, the return on your portfolio.
Okay.
Okay? But the variance of your portfolio, the risk, also is the sum of two products. But because of a rule in statistics, you cannot do it this way. You have to do it this way. It's A squared times the return on the stocks squared plus B squared times the return on the bonds squared plus 2 times A times B times the covariance of the two. It's just a rule. That's just the way it is. Okay? The end goal here is to find out how risky is my portfolio. That's your risk, standard deviation. Okay. In order to do that in matrix algebra, we're constructing a variance-covariance matrix, which together with the weights or the amount of money in each asset will give you the portfolio variance. Constructing that matrix, we're calling it R. This is the returns, actual returns, not expected returns. The transpose of R is just to swap the columns for the rows, which is just so that we can get something squared. Right? Because we need A squared and B squared and X squared and Y squared. The matrix of returns R to calculate the variance-covariance matrix V. Use variance-covariance matrix V to calculate the portfolio variance V sub P using weights. So you have weights and variance-covariance. Do we at least have an idea of what the hell I'm doing?
Do you have like any problems actually show like step by step with the numbers in there? Because it's just hard to understand this without like actually seeing like stock prices and everything like that.
All right, I'll put it together for you. That's a good question, Joe. I'll prepare something. So, how many of y'all looked at those slides and my notes since last time?
Mhm.
Okay, good. That's great. All right, look it. Now, I want to show you how we do this in R. James Johnson, can you see my R screen?
Yep.
So look. You guys follow along with me reading this code, okay? In R, anytime you want to put something in that doesn't get computed, you preface it with this pound sign or the hashtag. List all objects currently in the workspace. The command to do that in R is ls. If I run that command by pressing run, it does that. See down in the console here, ls. These are all the variables that have been assigned in my workspace. I want to remove all of those so that I have a clean workspace. rm list ls. That clears it. Clear the screen. Cat /F gets rid of everything. Get the working directory. I want to know what directory R is working in. C, users, M Gallagher, documents, econometrics, R data. Look at, if I do an explore in my computer, I'm telling R to set my working directory to this. C / users M. Gallagher documents econometrics R data. Users M. Gallagher documents econometrics R data. Our data is all the data that's going to be used in our textbook. So we talked about this. How many of you have gone to the student companion site of the textbook and downloaded the data and put it on your computers? So you know what I'm talking about, right? This isn't French. Yeah? So you need to tell R where that is. Yeah, because if you had something, for example, our studio here, if I said set the working directory and I change this to P and then I run, error. It can't do it because that doesn't exist. I got to take that P out of there and run the data. Okay?
I don't think you share your screen with us for that.
Thank you for telling me. It's very hard for me to remember that. Okay, look it. Can you see it now?
Yeah.
So I'm telling R, set my working directory where we do all our R work to see users M. Gallagher documents econometrics R data. That's where I put all my data. In my econometrics folder, in my documents, and that's me, et cetera, okay? This has to be exact. Notice this is the data file I'm going to load, varcode.txt. If I say properties and I say details, notice this C:/ users M. Gallagher documents econometrics R, right? Notice over here, it's C:/ users /. It has to be / in R, which is different than Windows, which is a /. Okay? So I set my working directory, run that line of code, load the data that I want. The data that I want is a file called varcode.txt. It's made up 3 different stocks for 10 time periods. So here I say data frame. This arrow and dash is read table, varcode.txt. Header is true. That means there are headers in the file. So look, if I went here and just let's have a look at this. That's in Notepad, right? I have stock A, stock B, stock C. These are headers. These are the time periods 1 through 10. These are the returns for each of these stocks for each of these periods. Yeah, 7%, 6.5%, 8%, 5.4%, et cetera, et cetera. What?
We can't see that.
Sorry. Now you see it?
Yes.
I opened up this file, varcode.txt. This is just information I made up. I made it up in Excel. And then I saved it as a text file. Right? .txt. Have you guys done that before? You can save Excel files. You could read an Excel file into R as it is. It's easier to read a text file. Okay? I don't expect you to know this like just by listening to me. You'll need to spend some time working on it and playing with it and doing it at home. And even then, unless you really want to learn this, you won't. And that doesn't mean you're going to fail the course. I'm here to teach it for your benefit. You can get through this course without learning this, but I don't want that to happen. Okay. We're back on my R Studio, right? I'm going through this code line by line. So I set the working directory here. Now I'm saying I want to load the data that I want. It's that data I just showed you. It's a text file I created in Excel and saved as a text file. Notice this environment window over here is empty. When I run this line of code and create a data frame, you'll see that populated. Here it is. I loaded it into R Studio. If I click on that, it shows me the text file that I loaded. So it's in R. I want to standardize that data by collecting means. When you standardize things, remember from statistics, you separate them from the means, right? You do the number minus the mean. So stock A bar, in other words, I'm calculating the average of stock A, right? Stock B bar is just as if we had X bar in statistics showing us that that is the average, right? The code is mean, data frame, $, column, stock A. Run that line of code and it should tell us. If you typed in now in the console, the mean of that column would be 0.0673. I do the next two columns. I want to create adjusted data with means subtracted from returns. So the adjusted data right here, I run that code. Now I want to create a matrix of adjusted returns called R. That's what I'm doing here. That's why we said this the other day. Construct a matrix of returns, R, the return on stock 1, etc., the transpose of that. Can you see what I'm sharing? Are you looking at my notes?
We're looking at the R.
This is what we're constructing in R. a matrix of returns. R equal to the return on 1, 1, R transpose. Create a matrix of adjusted returns called R. R combined columns of these adjusted numbers. Run that code. We have our matrix R. If you went down here and just typed R, those are the adjusted returns. Yeah? The returns minus their means.
I just had a quick question real quick.
Yeah.
Sorry to interrupt. So in your R Studio at the top in like the workspace, all the green, you just freehand typed that, correct? You didn't like insert that from anywhere?
I freehand type it all.
Okay. I just didn't know if there's like a shortcut to like insert it all, or you just like you typed it yourself.
When you guys, it's a great question, Connor, right?
Correct. Yep. Thank you.
Okay, we got Moodle.
Yeah.
Look at our code, right? It's right here. You can copy this. And then copy it on any number of the examples of code that I put up on Moodle. Just take it and copy it and paste it into your own R Studio. I recommend that you start every piece of R code with those lines because it clears out the memory of whatever's in R. Okay? Once you do it once, just copy it every time. You don't have to free type it all the time, you know? And then
Okay.
once you've written a regression in R, use the same thing to do your next project. Just change the variable names or whatever. I'm not asking you to sit here and write War and Peace in a tiny little window. Okay? But great questions.
Thank you.
So we created R here, right? We created the portfolio of returns. We're looking to create the variance covariance matrix. This is V, which is the transpose of R times R. V is the transpose of R times R divided by T minus 1. The transpose of R times R divided by T minus 1. I said number of rows of the data frame. That's T, your number of observations. Run that little bit. Create a vector of asset weights. Here, I just plugged them in. Weights is create a column 0.28, 47%, and 25%. So must sum the one, right? Weights in your portfolio, you want the risk of your whole portfolio. W, you're making a matrix out of what you just did. Run that little bit. Create VP. transpose of W times V times W. Use the covariance matrix V to calculate portfolio variance VP using weights. Weights transpose times V times W. Run the code. VP, tell me what it is. Some tiny little number, right? Convert the variance to a standard deviation. Variance is simply the square of the standard deviation. You all know that, right? Standard deviation is the square root of this. So it's 0.844%. Standard deviation of VP, which is your portfolio. That's 0.0844%. Does that sound like a lot?
No.
These are the made up numbers. They're all very similar. There's hardly any variance between them at all, right? It makes sense that it could be that small. So I told you in this, you can do this another way. The slides said you can do this another way. We just did it this way. So you have these slides, you have my notes, and you have the code to do it. But also in the slides, it says you could do it by doing it this way. Correlation. Define a correlation of returns. Matrix would have ones on the leading diagonal, blah, 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 blah. VP, the variance of your portfolio. Transpose of weights times S times C times S times W, the weights of your portfolio. I do that for you. Do the same exercise using a correlation matrix of the returns. C, correlation, degrees of freedom, method, so data frame, method, Pearson. Run the code, create a diagonal matrix, standard deviation values, create a diagonal matrix of that, call it D, calculate the portfolio variance using the correlation matrix instead of the variance covariance matrix, right? We're doing the same thing a different way, call it VPP. I got an error because I didn't have this whole thing highlighted. I'm going to do VPP. And then what is the value of VPP? It's a tiny number. Convert that variance to standard deviation. Standard deviation is square root of VPP. 0.844%. The same as we got. Okay? What I've done for you in R is this and this. I don't expect you to know the commands in R, but you have all of this on a recording. You could say, how did he do that? And look at the recording. That's the only way to learn, is for you to do it. And if you don't want to learn it, that's fine. I mean, I don't care, but I'm trying to give you everything you need to make this happen, and make you marketable people out in the workforce. And I think coding is one of them. And in my journeys, so that's my own code that I wrote and shared with you. But I told you that all of the exercises in our textbook, this book, are done in this book. And I've given you the book. Using R for introductory econometrics. Read it here. Waiting. Are you looking at the book right now? I mean, waiting for it to load? It loaded. Do you see the book?
Yeah.
All the code is here in the book. Our scripts. File names, working directories, resources, how to do things, how to code things, how to write things. And I just bought the exact same book, but doing everything, all the same things in Python. That's my mission this semester, is to convert the R so that students have an opportunity to use both R or Python. It's a freaking bargain. Okay. Tell me what you're thinking.
I just think a few more examples, or even if you wrote some notes of some examples, I think I'm a little bit more visual than reading the slides. So I think that would help.
All right. Yeah, we said Connor asked for the same thing, didn't he?
Yeah.
I'll do that.
I have a question. Will today's recording of class be on Moodle?
Yeah, of course. I do them all, don't I? Great question, Jesse. How come we can't see you?
I'm right now eating, that's why. You want to see the pizza?
You're eating pizza? Where? Where are you?
I'm at my dorm right now.
Okay, what else? What else? Talk to me. What are y'all thinking? Are y'all thinking, oh, this is a load of bullshit. I don't want to learn this.
I think we just have to practice a little bit and actually like when we see some of the examples that you write out for us, it'll help us a little bit more to kind of like correspond it with what we're actually going to be using it for in the future.
Yeah. Yeah, you can't learn it by watching me. But when you do your projects, you'll have to do them in R. So if you don't intend on learning R, hook up with somebody who's smart. I mean, let me rephrase that. Hook up with somebody who's willing to do it. Because you're all very smart. Okay. Are we done with that? Chapter 2 was the motivation for why we're doing this. And I'll put up later today, hopefully today or tomorrow, a more pertinent example that contains numbers. Okay? All right. That means so all that stuff I just showed you is right here, yeah? For your pleasure. That means we're going to start chapter 2 in the Wooldridge textbook. Notice I also put up here Wooldridge My Notes. So I open chapter 2, that's the PowerPoints. You looking at the PowerPoint?
No.
Now,
That was good.
I also want to show you my notes. See, this is on Moodle. These are all the PowerPoints with the things I would write. If we were in class, I would write all that stuff on the board. Okay? So let's start. The simple regression. Definition of a simple linear regression model. Explain the variable y in terms of some variable x, where you have your variable y, which we would call the dependent, the explained, or the response variable in a simple linear regression model. Beta sub 0 is the intercept. Sometimes this is called alpha. You may see it written as alpha. In your 7th grade days, where you had y is equal to mx plus b, this was b, right? The slope, beta sub 1, this is the m in that same equation, or, yeah, that's all. X is your independent variable, your explanatory variable, the regressor, whatever you want to call it, right? The error term U, some sort of disturbance, some sort of unobservable, okay? You should know the 5 parts to this equation. Very important to me. Interpretation of the simple linear regression model. It's a study of how y changes with changes in x. So beta sub 1 here, defined as the change in y over the change in x. How much does the dependent variable change if the independent variable is increased by 1 unit? That's your slope, right? If you change x, how much is y changing? The dependent variable y, how much is it changing if your independent variable x changes? As long as the change in your error, or u, over the change in x is equal to 0. It means these two must not be related. It's rarely applicable in practice, but the discussion is useful, so I can teach you. Pedagogical. Examples. Soybean yield and fertilizer. We have yield, some beta sub 0 or an intercept, beta sub 1 times fertilizer plus an error term. The error term comprises everything that's not in this equation. So we know that fertilizer is not the only thing that affects yield, right? It could be rainfall, land quality, parasites, etc. So the measure of effect of some unit of fertilizer on yield, holding everything fixed. Maybe it's wage, beta sub 0, beta sub 1 times education. And some error term made up of all the things that are not included in this. Labor force experience, tenure with current employer, work ethic, intelligence, etc. This is the slide we're looking at, and these are my own notes that I would write on the board. Fertilizer on yield. Beta sub 1 shows the effect of fertilizer on your yield. U, the error term, factors such as land, quality, rainfall, all the things that are not explicitly accounted for in this equation. Wage on education, beta sub 1, measures the change in wage given another year of education. The error term could be any other things, right? When is there a causal relationship? This is important. The expected value of your error term given some value of x must be 0. The explanatory variable must not contain information about the mean of the unobserved factors. X and your error term cannot be related. Does that make sense? For example, the conditional mean independence assumption is unlikely to hold because people who get more education are also likely to be more intelligent on average, and intelligence is something that would be in the error term. One of the first things we need to do is to assume the average value of your error terms is 0. Expected value of u is equal to 0. When we say expected value, all we really mean is the average of the previous values. yeah, you would expect your score on our final exam to be the average of all your other scores in the course. Am I right? So if we write something in expectations, in other words, E parentheses U, right? The expected value of U, that's simply the average of U. That's what that means. So then we could say that the expected value of U conditional on X is equal to 0. The measure of how two variables are related is their correlation coefficient. In other words, U and X must be uncorrelated. If they're not correlated, then they are not linearly related, which is what we need. They cannot be related. What this critically means for us is that the expected value of U conditional on X is equal to the expected value of U, which is equal to 0. The average value of U does not depend on X. Population regression function, the conditional mean independence assumption that we just talked about, implies that the expected value of Y given some value of X is equal to the expected value of beta sub 0 plus beta sub 1 X plus U conditional on X. But we know beta sub 1 of 0 plus beta sub 1 X plus E U conditional on X, we know this is 0. Therefore, the expected value of Y conditional on X is equal to beta sub 0 plus beta sub 1 X. Means the average value of the dependent variable can be expressed as a linear function of the explanatory variables. The expected value of Y conditional on X is a linear function of X. Using Y is equal to beta sub 0 plus beta sub 1X plus U. Putting this in expectations and conditional on X, the expected value of U conditional on X is 0, means that the expected value of Y conditional on X is this linear relationship. Linearity means a 1 unit change in X changes the expected value of Y by beta sub 1. The distribution of Y is centered around expected value of Y conditional on X, as in the next slide. Here, this is your regression, right? You have X, these are independent variables, X1, X2, X3. This is Y. This is your population regression function. The expected value of Y conditional on X is equal to this linear relationship beta sub 0 plus beta sub 1X. For individuals where X equals X2, the average value of Y is beta sub 0 plus beta sub 1 X sub 2, okay? It's useful to break this into a systematic component, expected value of Y conditional on X, or beta sub 0 plus beta sub 1X the part of y explained by x, and the unsystematic component u, the part of y that is not explained by x. One more. Deriving ordinary least squares. In order to estimate the regression model, we need data. A random sample of n observations. Here we have x sub 1, y sub 1, x sub 2, y sub 2, x sub 3, y sub 3, and the nth. Value of the explanatory value of the ith observation. And then y, of course, is the dependent variable. If I drew a picture on that slide, if we were in the classroom, I would draw this picture. We have x sub 1, y sub 1, x sub 2, y sub 2, right? All these different data points. Y, our dependent variable over here, is dependent on x. Given this linear relationship, beta sub 0 plus beta sub 1 x sub I plus u sub I. Perhaps x is income and y is savings. In other words, you would expect then if x was over here, some large amount of income, that y would be over here, and that this regression line would look something like this. Perhaps x is hours spent studying and y is your GPA, right? You would expect that if it was over here, this would be up here. If this was over here, this would be over here. Yeah? We're going to stop for today because I somehow feel like some of you may have become discouraged during our class today. And I don't want that. You know, if anybody is like struggling, please let me know. And I'm happy to try to help out, you know? So I don't want to overwhelm you. And I know I'm throwing a lot of stuff at you, you know? Like I said, you don't need to know everything. I'm just trying to teach you things that I feel would be good that you know? And, you know, some of you are going to embrace this and others are going to be like, why do I have to do this, you know? So I just figure let's go down the middle of the road and try and talk about some of it and try not to kill you at the same time. All right? So we'll call it a day. You know, I am very, very welcome to feedback. If anybody wants to shoot me an email or come and talk to me about, you know, how you're having problems with this or how I can do a better job, I'm very open to that. All right? All right, everybody. We'll see you Thursday.
Thank you very much.
Take care.
Thank you so much.
Thank you.
Thank you.
Have a good one.
Thank you.
Dr. Gallagher, I just have a quick question.
Okay.
So I'm trying to download our data set, and like it won't download on my computer, and I don't really know what I'm doing wrong because I went to the book companion site, and then I just pressed the link, and then nothing shows up on my computer, like where I can save it as a file.
What kind of a computer do you have?
It's a Microsoft.
Can you, would you share your screen with me?
Yeah, I can do that.
Let me just allow it first, okay?
Okay.
Uh, so first, I'm going to stop recording, all right?